Okay, welcome back, everyone. So we'll continue with the last lecture on celestial holography with Ana Maria.
Hi, thank you, João. So let me briefly summarize where we were at last time. So motivated by the fact that the subleading soft graviton theorem suggests that the Lorentz symmetry of scattering in four-dimensional asymptotically flat spacetimes gets enhanced to Virasoro, we started looking for so-called conformal primary solutions to the wave equation. Okay, so this was because we are trying to see if there is a way to reformulate scattering in four-dimensional asymptotically flat spacetimes in terms of observables, just recasted as an observable living on the celestial sphere. And we saw that there are indeed solutions to the wave equation which transform covariantly under the Lorentz SL2C. And in particular, we saw that one can construct them very explicitly. And in the case of massive particles, they take this form here in position space, or equivalently, they can be written as Fourier transforms, roughly speaking, of bulk to boundary propagators in ADS3. Now, starting from this representation, one can also take a massless limit and basically write down the associated conformal primaries for massless particles. And in that case, we saw that sort of this integral reduces to just a so-called Mellin transform. And so we arrived at this formula for a celestial amplitude, which we call A tilde. So this is a function now of n external dimensions, delta I, and n points on the celestial sphere. And it can be derived from the momentum space scattering amplitude. So say you have a bunch of massless particles labeled by momenta q hat times omega, and a bunch of massive particles labeled by momenta m times p hat, by doing this integral transforms. So this piece accounts for the transformations of the massless external lines, and this piece accounts for the transformation of the massive external lines. Now, by construction, we saw that the celestial amplitudes obey this transformation property. So they transform as correlators of conformal primaries. So I should say conformal correlators of primaries under the global conformal group. And finally, we gave an example of how this procedure works in the case of 3-point scattering of 2 massless and 1 massive scalar. And we saw that perhaps, well, not unsurprisingly, this amplitude turns out to be proportional to the standard 3-point function in a conformal field theory times some coefficient, which was computed, one can compute explicitly by performing these integral transforms, and it takes the form of this Euler beta function. So this is some kind of special function of the external dimensions. Okay, so today I want to discuss celestial symmetries. So we are going to see that these celestial theories enjoy quite a large class of symmetries, and we're going to start from the simplest ones, namely Poincare symmetries. So we have Poincare symmetry, and we'd like to understand how this acts on the celestial sphere, essentially. So there are 2 parts of the Poincare algebra. So one of them is generated by the Lorentz generators. So we have global, which we saw last time, that these act as global conformal symmetries on the celestial sphere. So you have global conformal symmetry which at the level of celestial amplitude is essentially the statement that we have we're defining, I'm going to define them in a moment, but these curly L subscript I generators acting on some n-point celestial amplitude, and their anti-holomorphic counterparts leave these celestial amplitudes invariant. So here I'm defining this curly Li to be sums from k equal to 1 to n of the usual, these would be the SL2R left generators acting on each of the external particles. And similarly, L bar I, sum from k equal to 1 to n of L bar ik, and these I indices run from -1, 0 to 1. So these are just the global overall, each external, each of them correspond to the six global conformal generators, and we're considering their action on each of these external particles. Perhaps just, okay, and there are some very explicit formulas for them, which one can derive basically by taking pullbacks of the standard Lorentz generators to scry plus or scry minus or to the celestial sphere. And one finds that they take the following form. So L0 is C dz plus H, L minus 1 is dz, and L plus 1 is Z squared dz plus 2 zh. So here I'm defining H as delta plus J divided by 2. And similarly, H bar delta minus J divided by 2. Then we have similar expressions for L bar, I's. Actually, let me just be consistent. L bar I with Z going to Z bar and H going to H bar. And these are very familiar from conformal field theory. And in fact, Maddalena already introduced these symmetries in her lectures, which is very nice. So in particular, these generate SL2R and can be thought of as just, if you're thinking about conformal field theory, as just dilations, translations, and global conformal transformations. The generators associated with these guys. Okay, so this is very familiar from conformal field theory, but now we have an additional global symmetry acting on the celestial sphere, which is inherited from both momentum conservation. So we have these momentum generators, which impose the following constraints on celestial amplitude. So we have some, again, defining some Curdy operators, Curdy P operators acting on AN is equal to 0, where these Curdy P mu's I'm defining as, again, the sum from K equal to 1 to N of P mu K, where for massless particles, these P mu K's or P mu I's take the following form. So epsilon I Q hat mu. So these are these null vectors I introduced last time, these guys. This is a sign plus minus 1, depending on whether we're considering an incoming or an outgoing particle on which this generator acts. And then we have this multiplication by this funny factor, which is a weight shifting operator. So what this does in particular is that if we act with this on some celestial operator of dimension delta I at some point zi z bar I, this gives back, okay, this is trivially just more proportional to epsilon I q mu zi z bar I. But then this essentially generates a shift in delta I. Okay, and this, I'm saying it's massless. It has the property that p squared is equal to 0, which is very easy to see because these q hats we saw last time, they are not. So you may ask, okay, this is a bit funny. How does this come about? Why do we have these weight shifting operators? Well, one way to see it, it's actually pretty simple, is by actually considering the action of momentum generators in the bulk. So in momentum space, we know that usual scattering amplitudes are eigenstates of the momenta on each external lines. So we have some external momentum pi hat. So this I'm distinguishing it from the celestial generator by putting a hat on it. So we have q. Now we have an amplitude, which is a function of any external momenta. And this gives back epsilon I, qi, it's a function zi z bar I. And times the momentum space scattering amplitude. But we saw, so this is omega I times this q hat of zi z bar I. Okay, where this is the energy of the external of this whatever massless particle we are acting on. And now it's very easy to see that it is this this multiplication by this factor of energy that on the celestial sphere maps into a shift of the weight. So to see that, okay, I'm just going to do it explicitly, but perhaps it's obvious. So to see what the action is on a celestial amplitude, one can just consider the Mellin transform. So we have product from j equal to 1 to n, integral from 0 to infinity, the omega j to the delta j minus 1. And then we have the action in momentum space of this generator pi acting on A as a function of q of all of the external q1 to qn. Okay, but I just wrote down what this action is, so one can immediately see that in fact this becomes just epsilon I q hat I, and then a product from j equal to 1, but j different than I now, to n of integral 0 to infinity the omega j to the delta j minus 1. But then we have the ith leg comes multiplied with a power of omega I from this action of momentum on the leg I. So the Mellin transform for the ith external leg, sorry, this is omega I, delta I minus 1. Here we have delta shifted by 1, okay? Delta I is shifted by 1. And this, of course, is now times the A of Q1 to Qn. And this is precisely what I wrote down before. So it's epsilon I Qi times the celestial amplitude, where all the weights are, delta 1 are the same as before, except for the ith dimension, which gets shifted by 1. Okay, so this is how momenta act on the celestial sphere. For massless particles, they act as just weight shifting operators. We're going to see in a moment how to generalize this for massive particles. But let me just say that now the statement of momentum conservation, so essentially these equations, then explicitly map into a relationship between celestial amplitudes involving operators of shifted weights. So in particular, bulk, momentum, conservation maps into the following relation among celestial amplitudes. So we have, this is essentially P1 acting on AN, and then P2 acting on A tilde N is delta 1, delta 2 plus 1, delta N, plus a bunch of other terms coming from all the other momenta acting on all of the other external legs, plus A tilde N, delta 1, delta 2, delta N plus 1. And by momentum conservation, so we know that the sum of a Pi from I ranging from 1 to N has to be equal to 0. Okay. And this relationship is actually quite non-trivial. And it's certainly not something we're familiar with from, for example, two-dimensional conformal field theory. And we'll see in a moment that this can be used to completely fix 3-point celestial amplitudes. And it also can be used to constrain 4-point celestial amplitudes. Okay, but before going there, let me just write it down. So here, for simplicity, I just looked at the action of these massless generators. It turns out that for massive particles, they take a more complicated form. So for massive particles, we have these P mu's being, of course, proportional to these factors of M, but now we have two terms contributing. So one of them looks something like this. Let's see, bar plus coordination conjugate divided by delta minus 1 plus Q mu dz bar 1 delta times e to the minus d by d delta, and then plus, I did something to see here. So I have two terms. One of them is multiplied by a lowering weight operator, and the other one is multiplied by a raising operator. Okay, so this term is a bit funny, but it has to be here. To ensure that essentially, in this case, P squared is equal to minus M squared. And of course, one also has, these generators also have to obey the Poincare algebra. So in particular, momenta have to commute with one another. And you can check that actually this expression satisfies these properties. And also, of course, it also obeys the standard commutation relations with the Lorentz generators. So you can check, and this has been worked out if you want a reference for this by Law and Zlarnikov. This was 2019, and there is a follow-up generalization to the case where spinning particles are present as well, in which case this expression becomes even more complicated. So the corresponding generators acting on spinning particles are also going to involve terms which shift the spin on the celestial sphere. So you can see that, well, in fact, we will see in a moment that there is quite a rich structure. So these additional global symmetries on the celestial sphere are going to impose some non-trivial constraints on celestial amplitudes. Okay, so just to summarize, Poincare on the celestial sphere has two components. One of them is usual SL2C generated by L0, L plus minus 1, L0 bar, L bar plus minus 1, which is the usual global conformal symmetry in 2 dimensions. So we're going to see in a moment that the way this constrains celestial amplitudes is the same way in which conformal correlators are constrained in conformal field theory. And the second one is this additional global symmetry coming from translation symmetry, which for non-zero M and scalars consists of these generators, which have a piece that lowers the dimension, and another piece that raises the dimension of the operators. So I think this is a good point to stop if people have any questions, because what I'm going to do next is use essentially these additional constraints coming from this momentum conservation to show you how one can constrain how celestial 4-point functions are constrained, how they differ from what one might expect from just conformal field theory. Okay, so if there's no questions, let me move on and discuss constraints on 4-point functions. So Madalena already made our life easy because somehow my iPad is frozen. Okay, the 4-point functions will take the following form. So we have this prefactor, which is going to be a conformally covariant prefactor, and some function, which is just a function of the cross ratio. So this follows from just SL2C. So any celestial 4-point function has to take this form. And here it's convenient to define the cross ratio as Z13, Z24 divided by Z12, Z34, which, okay, from the bulk point of view is just the ratio of T divided by S, where T is the momentum transfer, and S is the center of mass energy. So in a bulk 2-to-2 scattering process. Okay, so here I'm going to take this kappa to be the conformally covariant cross ratio, which is symmetric under exchange of all 4 external points. This was not, for example, what's usually done in Bootstrap. One usually just takes this guy to be the conformally covariant prefactor, which is just invariant under exchanges of pairs of external lines. But we're going to see in a moment that, I mean, these two, of course, they will differ by some function, which is just a function of the cross ratio. But today, I mean, for what I'm going to do next, it's convenient to just choose the former. So this, just to be very explicit, this takes the following form. So Zij H divided by 3 minus Hi minus Hj. And similarly for Z bar Ij, H bar J, where H I'm defining to be the sum from 1 to 4 of Hi, and similarly for H bar. Okay. And the reason why I'm choosing this why I'm choosing to put my celestial 4-point function in this form is that this symmetric conformally covariant prefactor is actually also invariant under translations. So function invariant, which is essentially the statement that if you were to sum over j from 1 to 4, k hj plus a half, h bar j plus a half, for all the other external with just delta, essentially I'm just shifting delta j by 1 for all other external dimensions fixed. This turns out to be equal to 0, so you can check this. This is not a property of the other choice for conformally covariant cross ratio. So now this property makes our life very easy. Now we want to see how Poincare, so how momentum conservation actually constrains this function of the cross ratio only. So this you can check. But what this tells us is that this fact, so this plus translation invariance of 4-point function, as I wrote it down before in terms of a relationship involving amplitudes with shifted weights, then just implies that these functions g obey the following relations. So g hi plus a half, h bar I plus a half of z and z bar is equal to g of hj plus a half, h bar j plus a half of z and z bar for all I and j. So essentially, for example, you'd have a relationship of the form g of delta 1 plus 1 with all other external dimensions fixed is equal to g of delta 2 plus 1 with all other external dimensions fixed. And so on. You can, same for 1 and 3, 1 and 4, and so on and so forth. And it turns out the set of recursion relations, if you put them all together, they imply, and again, you can check this, that this G, which in usual conformal field theory can depend arbitrarily on the external dimensions. In this case, it can only depend on the external dimensions through their sum. So this is going to be G of delta 1 plus delta 2 plus delta 3 plus delta 4. And j, so I can trade, by the way, so by the relationship I wrote down at the beginning, I can trade h and h bar for delta and j. And so we have the following constraint on this conformally covariant prefactor. So g can only depend on the sum of external dimensions. Okay, now in addition to this, just using some, also from momentum conservation, we also find that G has to be proportional to a delta function, which fixes the cross ratio to be real. So this is because the 4 particles scatter in a plane by momentum conservation, which crosses the celestial sphere at a circle. And both so let me just emphasize that both this property and this property are very unusual for if one thinks about just standard 2D conformal field theory. Again, there were some questions on the Slack. Perhaps we can discuss them in the discussion session, but these are two ways in which celestial amplitudes differ from standard conformal 4-point functions. Now, okay, so this is the general form a conformal 4-point function can take, just using this additional constraint from momentum conservation. Now, let's look at another example, which is this case of scattering of two massless and one massive scalars. So this is the amplitude we explicitly computed. I wrote down a formula for before, so at the end of last class. Now I'm going to derive the same formula, just purely using these Poincare constraints. So of course, SL2C tells us that this amplitude has to be proportional to this 3-point structure we saw in Madalena's class. So delta 2 minus delta 3, and so on. So here I'm glossing over some subtleties where one just has, for example, if this guy was just a massless particle instead, then the life wouldn't be so easy. But let me just, for now, just ignore the subtleties and perhaps discuss them in the discussion session. But this is something which is consistent. This is a structure which is consistent with SL2C. And so now what we want to do is to see how, if we can, what this global transition symmetry additionally tells us. And in particular, we're going to see that it tells us something non-trivial about these 3-point coefficients. And the way to see that is to impose momentum conservation. So as we did before, so let's act with P1 plus P2 plus P3 massive. So again, these are the massless generators, and these are this one is the massive one. They differ, as we saw. 2 of them involve just these lowering dimension parts, and the massive one involves both lowering and raising dimension components. So we want to ask that the sum of these 3 momentum generators acting on this amplitude is equal to 0. Okay, and this is, again, if you do it by hand, it's a bit lengthy calculation, but you can also just take, put it in Mathematica. So you can just define these generators, the z dependence of this 3-point function, and then just ask Mathematica to essentially expand this. And generically, there's going to be some relation of this form. So there's going to be a sum over monomials involving zi's and z bar i's. So we're going to have terms like this, same involving z2 and a bunch of other terms is equal to 0. And of course, this relation tells us that the coefficients of all monomials in zi and z bar I have to vanish independently. And magically, this turns out to just reduce to 3 constraints. And let me just write them down so you get a flavor of the kinds of things one finds. So we have delta 1, 2 squared divided by 4 minus delta 3 minus 1 squared divided by 4. C delta 1, delta 2 delta 3 minus 1 plus delta 3 minus 1, C delta 1, delta 2, delta 3 plus 1 is equal to 0. And then there is something which looks like 4 delta 3 minus 1, C delta 1, delta 2 plus 1 delta 3 plus M epsilon 3 delta 3 minus 1 minus delta 1, 2, C delta 1, delta 2, delta 3 minus 1 is equal to 0. And the similar relation with 2 and 1 interchanged. And again, magically, and again, this has been shown in these papers by Lorenz-Lodnikov, I mentioned before, that the solution to these recursion relations is essentially uniquely the following. So this is, again, a function of the couplings and the mass, but times this Euler beta function of these arguments. So this is exactly what we found by explicit computation before, as it should be, because, you know, everything should be consistent. But here, I just want to draw your attention. So again, in delta 1, 2 is delta 1 minus delta 2. So I just want to draw your attention to the fact that, okay, on the one hand, one can compute the celestial 3-point function by just putting it into the celestial basis by performing these integrals explicitly. And if you perhaps you tried, and you might have found that it's, you know, you have to do some integrals, and it's not, you know, even in the simplest example of 3-point scattering is not a trivial calculation. But here we just see that just by imposing Poincare symmetry, one ends up instead with a set of recursion relations, which, if one is clever enough, or perhaps with the help of Mathematica, can be used to arrive at the same result. And in a moment, we're going to see another example where one can use celestial symmetries to, again, say, well, recompute some things you perhaps knew from momentum space, but in a much, much simpler way. So again, now that we discussed Poincare, the next thing I want to discuss is conformally soft symmetries. So these are going to be an additional set of constraints celestial amplitudes have to obey, but let me pause to see if there is any questions at this point. Yes, Antonio?
Hi, so this is probably too much of a worry, but I'm a bit worried that since we said that the dimensions of our amplitude should be in the principal series, so 1 plus I mu.
Yeah, that's
I'm
a
bit
great
worried
point.
that the shifts are taking us away from there.
No, yes, and yes, you're totally right, and I'm glad that you asked this question because I forgot to mention it, but indeed, they shift you off the principal series, and I would say that at this point, well, the fact that they have to lie on the principal series was just a constraint which came from imposed. Yeah, it was one choice of solutions which form a basis to the scalar wave equation. For example, this is how I presented it, but it's not it's by far not obvious that that's the only unique choice of basis one can define, and in particular. Yes, we just saw the translations shift you off the principal series, and they certainly, for example, would appear such operators of shifted weights, for example, appear in conformal block decompositions of celestial 4-point functions, as one would expect from translation invariance. You're going to see in a moment that soft operators, so even this stress tensor I defined last time, constructed from the subleading soft graviton theorem, it's an operator of dimension 2 and spin 2, this TZZ I defined last time. So of course, that's also not on the principal series. There is a whole tower of soft operators which have negative, integer and half integer weights on the negative sort of real axis. They appear at various negative integers and half integers. And those are also not on the principal series, but nevertheless, there could be a sense in which one could rewrite this the complete set of operators, which are of the form 1 plus I lambda, in terms of just perhaps either just positive integer weight operators or negative integer weight operators. It's been argued, there are some papers, I can send you the references later, where some people have argued that there are these alternate bases one can consider. But I would say that it's still like what the best choice of a basis is in this case. I would say that it's a problem which has not been completely solved yet. But yeah, I'm certainly not going to restrict to operators on the principal series here. Thanks for the question. Anything else? Okay, so let me move on to conformally soft symmetries. Okay, so from lecture 1, we saw that there is this relationship between soft theorems and symmetries of the S matrix. So in particular, we saw that, so I did an example, namely the insertion of a subleading soft graviton theorem generates the word identity associated with an insertion of the stress tensor, but there are simpler versions of that statement, and perhaps one of the simplest ones is that the soft photon theorem, whereas by a soft photon, I just mean the limit as omega goes to 0 of omega and say dagger plus. So these are creation annihilation operators associated with the photon. Minus omega x hat. This is a soft photon. I can call this JZ, and what the soft theorem tells us is that, okay, insertions of this JZ operator into the S matrix, which one can just recast as, one can just label the asymptotic states, I mean momentum space at this point, as insertions of operators of energy omega 1 inserted at some point Z1 on omega n zn bar. So this can be shown to be equal to the sum over k from 1 to n of qk divided by z minus zk of O1 to On. Okay, so this suggests that the soft photon should somehow be interpreted as some kind of current on the celestial sphere, because this is just the word identity of a U1 current. So so this is just, this is a momentum space statement. And I want to ask, I want to recast this as a relation between, or a relation on the celestial sphere. And naively, it's not super obvious how one would recast this as an identity between celestial amplitudes, because the soft photon, right, is defined as the zero energy limit of a particular photon in the bulk. But we just saw that for a photon is a massless particle, but we just saw that the massless particles, if one wants to put them in the celestial basis, one has to integrate over all of its energies from 0 to infinity. So what does it mean to take omega to 0? from the celestial point of view, right? It has to map onto some kind of statement about dimensions. So we'll see exactly what this translates to in a moment, but let me just write down what I just said. So what does it mean to take omega to 0 in the celestial basis? One can make an educated guess by thinking about CFTD, some d-dimensional conformal field theory, where we know that currents, so we see that this sort of behaves like a current, but we know that currents in conformal field theory saturate unitarity bounds. So in particular in CFT2, Madalena wrote this nice relationship. We know that the dimension of the current, of a current of spin J, is equal to its spin. So a candidate, so this suggests that a candidate for such a conformally soft photon or current in the celestial theory is a positive helicity delta equal to 1 photon. So, okay. So to see this more explicitly, so indeed, okay, this guess turns out to be correct. And one way to see this is by starting with the formula for the Mellin transform of this photon. So we have integral from 0 to infinity over the omega to the delta minus 1, O plus omega z and z bar. And let's consider the limit as delta goes to 1 of this expression, but let me not just take delta to 1, but let me take the limit as, well, let me take delta to 1, but also multiply this operator by delta minus 1. So it's, in a moment, we're going to see why I'm doing this. So this is now going to be the limit. I can just use this formula to show that this is the limit as delta goes to 1, integral from 0 to infinity. And then we have delta minus 1, omega to the delta minus 1. Okay, and now there is a funny formula for this limit. There is a funny formula for this limit, which is due to the following identity. The limit is epsilon goes to 0 of epsilon divided by 2 x to the epsilon minus 1 is a delta function of x. So that implies that this limit is equal to just 2 integral from 0 to infinity the omega delta function of omega times O plus omega z and z bar. And now this is just 2 times a half times limit as omega goes to 0 of omega O plus bar. So this is just, it's nothing but from the bulk point of view, this is indeed a soft photon. But notice, we also notice that a pole, right? The reason I was multiplying by omega and taking this limit as omega goes to 0 is that the current, usually the soft factor, as we saw in the first lecture, it has a pole in omega. So you just want to remove that pole because, of course, this is a momentum space statement. It doesn't involve this 1 over omega factor here, right? So this current is defined by taking the limit of the soft photon's energy, of the photon's energy going to zero upon multiplying by the energy. So similarly, we see that this pole, so on the celestial sphere, this pole in omega maps onto a pole in the celestial amplitude at the delta equal to 1. So we also arrive at the conclusion that celestial amplitudes have poles at delta equal to 1. But in fact, they turn out to have poles at all negative integer deltas. So there's poles, there are actually soft currents associated with all delta equal to 1, 0, -1, -2, and so on and so forth. And one way to see this, okay, I think I'm not going to have time to do this right now, but can be seen by considering just like I did before, the limit as delta goes to -n now with n -1, 0, 1 dot of delta plus n O delta plus inserted at the z and z bar. And this particular limit picks out, under some assumptions, okay, it's a bit subtle, but it picks out essentially the coefficient of the omega to the n term in an expansion of O omega z and z bar around omega in the low energy limit. Okay, so it's going to pick out these coefficients. So these this is again the bulk picture, and in particular, as two examples, the subleading soft photon corresponds to the following celestial operator. So limit is delta goes to 0 of delta times O plus delta z and z bar. A subleading soft graviton corresponds to the limit as delta goes to -1 of delta plus 1 g plus delta z and z bar, and so on and so forth. So there is actually, so as I said, there is an infinity of soft currents obeying an interesting algebra and this has been studied in this work by Guevara, in which Tate and Strominger I'm going to pause for a second because I have my window open and it's pouring right now. So let me just. Okay, I'm really sorry about this, but it's a good point to stop for questions. So do people have any questions about these negative dimension operators? It's of course it's it's unusual to think about such objects in usual conformal field theory, but nevertheless, we just saw that they exist in these celestial conformal field theories. And okay, in the last 5, if there are, please feel free to interrupt if there are any questions. But in the last 5 minutes, I want to tell you how.
Let me just ask a question. Sorry,
Yes.
I'm confused because so we know that we will have infrared divergences once we compute loops in these massless theories.
Right.
So how do they manifest here? You're still not taking that into account, right?
No. So at this point, I'm just I'm not really taking that into account, and I would say that it's still. I think it's. I mean, it's very much of an open problem. There are some proposals of how to define celestial amplitudes, which would correspond to infrared finite quantities in the bulk, and this involves the story about dressings and so on and so forth. But at this point, I'm not really. In particular, there are also some open questions about in particular, one would have to understand how to treat correlation functions involving multiple soft particles, and that story has not been nailed down yet. But
okay.
Yeah, that's a great question.
Thank you.
Okay, so we just have this infinity of symmetries, but one application is that one can use subleading and sub-subleading soft theorems to constrain operator product expansions of gluons and gravitons. And the way this works, let me just very, very briefly sketch it, is that we know that from a bulk point of view, it's not just the soft limits that are universal, but there is also the so-called collinear limit, in which 2 particles become collinear, in which case the amplitudes again factorize from the bulk point of view, which from the celestial point of view maps onto a statement about the operator product expansion. So if we have, for example, so here I'm considering gluons, where A and B are going to be color indices, and I'm taking them to be positive helicity ones. And this, from general arguments, essentially soft, sort of from the soft theorem, we know that the leading pole in Z12 has to take the following form. So, well, this OP is going to just have the leading term in the limit Z as Z1 goes to Z2 is going to be the following. And then this is multiplied by O delta 1 plus delta 2 minus 1 plus C. Oh, and let me be precise. Z2, Z bar 2. And essentially everything here, and then there's going to be other contributions from descendants and perhaps other primaries, but this can be argued to be the leading contribution. And if the fact that there is just a pole here, and SL2C essentially fixes these dimensions. So up to an unknown coefficient, this is the OP, and Madalena again already described how one writes down such formulas. But now the idea is that one can use the subleading soft gluon theorem to constrain this C delta 1, delta 2. And I actually don't have time to do this right now, but it turns out that one can map the subleading soft theorem into a transformation property of positive and negative helicity gluons. So this is going to be something like some kind of differential operator times I F A B C O plus minus C delta minus 1. So this is a feature of, if you put together what I said right before this, you see that subleading, the action of the symmetry associated to the subleading soft gluon theorem is going to lower the dimension of this operator. And similarly, there is a negative helicity version of this. It's minus A delta. And you can find formulas for these in the notes. And there is also a reference I can give later for all of this. But the point is that now we impose that this is a symmetry of the OPE. So of the OPE I just wrote here. So in particular, we have a relationship of the form something like delta D O plus A delta 1, O plus B delta 2, plus O plus A delta 1, delta D O plus B delta 2. So this is acting with the symmetry on the left-hand side of the OPE, has to be equal to IFAPC Z1, 2, and then C delta 1, delta 2, minus D O plus C delta 1 plus delta 2 minus 1. And then plugging in the formulas for the symmetry action on both sides, it turns out that first, essentially on this side, by first acting with the symmetry and then taking the OPE is going to give rise to formulas involving these OP coefficients, but at shifted values of the dimensions. And in particular, at the end of the day, one finds a relationship of this form. So we've already seen some recursion relations before, but here is another one. So we have something which looks like this. Delta 2. And this has a unique solution. Okay, yeah, so the solution actually is uniquely fixed by also you have to invoke the leading soft theorem as well to fix an overall coefficient, but essentially one finds there is a theorem which essentially tells you that this recursion relation has a unique solution up to a constant, and that constant can be fixed by the leading soft theorem, and it looks something like this: beta delta 1 minus 1 delta 2 minus 1. And this is this is the leading OP coefficient in the operator product expansion of two positive helicity gluons. One can do a similar analysis for gravity, which again is going to give some formulas for these leading OP coefficients, and these have been worked out, and also in some other papers they've been worked out to subleading order, and there is quite a rich story here. But let me just point out that here I'm just using symmetries to derive some fact, so about scattering amplitudes in the bulk, right? So the statement also maps by inverse Mellin transform to a statement of about collinear limits of scattering amplitudes. And in particular, if this collinear factorization of in gravity took quite a while to be established. So in fact, it's only been, I think, formally proven 10 or 20 years ago. But here we just see, okay, I've done the gluon case, but you can run through the same analysis in gravity, and you land on essentially this splitting function immediately just by solving some recursion relation. So there may be some potential for kind of simplifying or learning something new about, for example, scattering amplitudes in the bulk. So since I'm out of time, well, I had some comments about where all of this is going, but you know, I think a lot of these ideas are really tied to all the other lectures we had so far. So for example, it would be very interesting to understand if one can use Bootstrap to say something about these celestial 4-point functions, for example. And in particular, one would have to generalize those ideas to the case where one has Poincare symmetry and so on and so forth. Another interesting thing would be, which kind of ties to Matthias' lectures, is whether there is an intrinsic kind of string construction for all of this. And in fact, there's been a paper where where the authors argued that the celestial sphere gets pinned to the string worldsheet. So there may be some kind of connection there. We don't really understand what happens if you're black holes. That would also be very interesting to understand what happens from the celestial point of view. And finally, there is this one big question, namely, what are the symmetries of gravity in asymptotically flat spacetimes? And I would say that we don't really know the answer to this question, but we're hoping that perhaps the ideas here would help in kind of making some progress in answering that. So with that, thank you very much. And if there's any questions, I'm happy to take them.
Thank you. Thank you very much for these nice lectures. And yes, the floor is open for questions. Well, while people think about the questions, I have some. So you actually mentioned Matthias. I find it curious that both you and Matthias are talking about CFT correlation functions proportional to delta functions, which is, as you said, very strange. But both of you are talking about that. So perhaps there is a connection that here you would have to use this kind of spectral float representations, and that, okay, it's pure spectral.
Yeah, that would be. Yeah, I need to understand that, so I'm going to study it a bit in more detail. But that does seem to. It would be very interesting if there was some kind of.
So let me ask you a more concrete question. It's more of a clarification. Maybe you already said it, but so when you do this analysis of asymptotic symmetries in different space-time dimensions, so do you get exactly infinite dimensional groups in the same dimensions where you have infrared divergences, where the amplitudes are not finite and they're infrared divergent? Is there like a one?
In higher dimensions, right, there are no infrared divergences, and I think that's consistent with the fact that both the BMS, like what one would call the BMS group, and the analog in QED, it just reduces to Poincare in higher dimensions. But having said that, I mean, it's not. There is still a sense in which there is an infinite dimensional asymptotic symmetry group, for example, in higher dimensional gravity, but it acts at the subleading. It's so-called Coulombic order in a 1/r expansion. So there is a derivative order, which is the most leading one. So there, everything is frozen, and it's been shown by Wald and collaborators that there is BMS just acts trivially. So there, in other words, you just Poincare that order, but there is a non-trivial sort of symmetry group. In what way it's a symmetry, it's not fully well understood, because if you compute the charges associated to those symmetries, they also fall off with R. And so as you take R to infinity, those charges vanish. But nevertheless, up to this prefactor, one can show explicitly that there are soft theorems in higher dimensions, and in fact, they motivate the existence of these charges, and one can kind of still formally define these charges for large R and ask that they are a symmetry. They impose a symmetry on the S matrix, and one can show, and it matches, everything matches just fine. You can show that you recover the higher dimensional versions of the soft theorems. And there is also an associated memory effect. But again, it appears it's just a more subleading order in 1/r. And the fact that I think they formally vanish as R goes to infinities is tied to the absence of these IR divergences ultimately.
Right. Thank you. So Leonardo has a question.
Hi. First, thanks for the amazing lectures. And I have a question related to, well, the soft theorems, they get mapped to these conformally soft theorems, right?
Yes, that's right.
Yeah, so my question is basically, well, I am aware that there are some magnetic corrections to the soft photon theorem. So have these magnetic corrections been mapped to the celestial amplitudes?
Oh, to the celestial amplitudes. So no, as far as I know, no. I think it's still an open problem. But Andy has a paper about magnetic corrections to the soft theorem in momentum space.
Yeah, that's the one I was.
Yeah, it has not been fully nailed down, for example, what the currents are, like what the associated symmetry is on the celestial theory, as far as I know.
Okay, so the one you talked about is the standard electric soft photon theorem, the standard one.
What I've been talking about here is just the usual electric. Yeah, one can have these magnetic soft theorems also if there's magnetic monopoles or something like that. In gravity, it's even more subtle because there are these dual super translations as well, which again, they're quite mysterious. I don't have many intelligent things to say about that because I haven't thought about that case very much. But yeah, people have been trying to understand them, but I'm not sure if there is something about celestial amplitudes in particular having to do with that story. Most of the analysis are asymptotic symmetry analysis, phase space, what the phase space is supposed to be, what the charges are, how everything plays into, what the algebra is, but yeah. But anyways, I think all of these developments can probably be mapped onto statements about celestial amplitudes. I mean,
that's what I thought. And I have another question. It's about these operator product expansions. So if you study the OP of that stress tensor you have defined with itself, would it reveal some central charge?
That's a question everyone asks. It's a great question. No, I mean, at least in all of the calculations that have been done so far, the central charge is equal to 0.
Okay.
I don't know. On the other hand, there are actually, and again, this I don't understand very well. There are, there's the stress tensor, which can be thought of as the shadow transform of a graviton, but there is also the subleading soft graviton itself, which is what, for example, one would use in constraining these OPEs. So I don't think people understand. There's, in some sense, perhaps there's two stress tensors. I don't know. The stress tensor in this
it's somewhat confusing. It's somewhat confusing for me to have two stress tensors.
But perhaps they have. I think that there were some speculations about how their OPE may have some kind of central term, perhaps. I don't know. As far as I know, yeah, there has been no proposal of a non-zero central charge.
Okay, thanks.
Igor?
Oh, hello.
Hi.
Can you hear me?
Yes. Mm-hmm.
Okay. Just two simple questions. Okay, we have two lectures in this school about ADS3 CFT2, one by Matthias and now your talk. But the case of Matthias is about proving the ADS-CFT in the case of string theory. Here, you do not need anything about string theory itself. Namely, you do not need a higher dimensional space and then make a compactification.
So first of all, let me say that I have not really talked about ADS3CFT2, and in particular, okay, somehow that can be invoked by using this slicing of Minkowski space, which to some extent motivated the definition of these conformal primary wave functions. But in what way, and I also sort of said on Slack, it's really not, I think what we're doing here is much more than just ABS3 CFT2. And the reason why that is because if you think about scattering in the bulk, so for example, just 4-point masses scattering in the bulk, right? The point at which these 4 points are going to meet is certainly not, does not have to lie on an ABS3 slice in the slicing I presented. So it can be anywhere inside the bulk. And that's one reason which indicates the fact that, of course, it's not just scattering in ABS3 we're looking at. And the second thing is that, as I just argued, perhaps not very clearly, but 4-point functions in the celestial conformal field theory, they're all multiplied by these delta functions in Z minus Z bar, which again is not what one usually would get from a computation of a Witten diagram, for example, in ABS3, right? So it's not, if I were to make a connection to ABS CFT, perhaps more promising, at least to me, seems taking the flat space limit of ABS4 CFT3, right? In which case it corresponds to some limit in which the dimensions of the operators in the conformal field theory are taken to be very large. And perhaps one can argue that somehow in this limit, something, I don't really understand how this would work, but somehow the CFT3 kind of localizes on just a 2-dimensional slice, or I don't know. I don't really have, maybe João can comment.
This is a very good suggestion, because indeed the structure of this limit, you take all your points to 2 spheres, right, at global time, whatever, minus pi/2 and pi/2. So you get like 2 copies of the celestial sphere, like you have the square minus and square plus.
Right.
The worst really is probably you'll get square plus and square minus some kind of thickened version of these 2 spheres at pi/2 and minus pi/2.
Yeah, I would really like to explore that. I started thinking about it a couple of months ago, but I haven't. I got distracted with other things. I think it's very interesting. I think it would be very interesting to
the motivation for which I asked the question is simply that, let's suppose the conjecture of celestial holography is true for quantum theory of gravity living in the book, being dual to CCFT. Okay, and string theorists believes that they have the only self-consistent theory of quantum gravity. So there must be a way of reconciling the celestial holography program with this point of view about quantum gravity, unless you can formulate a quantum theory of gravity in asymptotically flat space-times without having to invoke the full string theory machinery. So that was the motivation for my question.
I agree with what you're saying. I think it has not been, it's certainly, you're asking a very big question. So it's a very ambitious one. And I think hopefully, so I should also say that most of the things I presented in this lecture, in this sort of lecture series, they're really state of the art in this field, right? It just started a couple of years ago, sort of the celestial holography story, and we really just don't understand that much about it, which I think is part why it's exciting to think about these things. So, but I don't have that much more to say about, well, right now, I mean, ultimately we'd like to understand all of this much, much better. But I think it just has not been enough time since people have started thinking about it. And I'm hoping that at least some of you will join this perhaps program.
So yeah, so there's still a discussion session in the afternoon. So I suggest that we postpone. Well,
Okay.
Aswin, is it a short question, Aswin?
Oh,
It might, I don't know. So I just wanted to ask, is the double copy relations shown to be true in the celestial holography?
Yeah, what about them? There have been some papers, I can suggest some references about the double copy, but I don't, it's again, they're very recent papers, and yeah, I mean, one can, you know, scattering amplitudes in the bulk, they obey all sorts of relations, and you can ask the question, okay, what do these relations map to on the celestial sphere? And there is a celestial version of the double copy relation, which has been derived in various papers by Poom and collaborators, for example. So Eduardo Casali, also Atul Sharma. So there are some references. So I can send on Slack a bunch.
Okay. Thank you.
Okay. So let's officially conclude this third lectures by thanking Anna with a big round of applause.
Congratulations for the talk. Thank you.
Yeah, thank you very much. And
thank you for asking so many questions and inviting me.
So keep some questions still for the discussion session this afternoon. And I guess we can close for lunch or something else, depending on your time zone. Thank you. Thank you very much.
Thank you.